Hello, it's David. Now in a previous video I built this little dual drop IDE 2.5-inch drive adapter for the Atari Falcon. Quite straightforward, master and slave connections and a host connection here. However, I also experimented with adding a second host connection, not to be used at the same time, but that incorporated a byte swap, because when Atari built the Falcon, they stored their data on the IDE device in native Falcon format, which is Big-Endian, and the standard today is pretty much Little-Endian. So if you take if you have an adapter card, either a CF card adapter or an SD card adapter plugged into here, and you unplug your CF card or your SD card, you plug it into your PC, you can't natively read it. You have to do a conversion, image the drive, convert it before you can load it up in an emulator, or even just access it from Windows, Linux, MacOS. What the byte swap was hoping to do was to alleviate some of that burden, so that you could actually plug it into the PC, take it out there, plug it into the Falcon and boot up. And it does work to a certain extent. The main issue is that swapping the data lines, it doesn't just affect the data stored on the disk, but it also affects all the registers on the adapter and also drive information. So how the size of the drive. So unless you have a driver that's specifically tailored to cope with what they call twisted cable, this byte swapped arrangement, then you don't really get any benefit. Now Emutos has that, and I demonstrate in the video linked up here how that works and how that has an effect on the speed. But I was hoping we could do a slightly better job. So here we go. It's time for another new project. This, back from PCBWay, is version 2 of my Atari Falcon dual drop adapter with some added smarts. Yes, it's another CPLD project. I'm afraid they're my hammer and everything looks like a nail. They're just so versatile. So what we're going to do is we're going to add this Xilinx XC9572 in CPLD in a 64-pin package. We've got a 3.3 volt regulator. This is an LM1117, although we support 2 different types on here. Information will be in the project linked in down below. We've got an activity LED and a 1K resistor. We've got 6 100 nanofarad multi-layer ceramic capacitors. We've got a 2mm pin header. We've got a 2mm header receptacle. This is 44 pin. This is supposed to be 44 pin, but I couldn't find any, so these are 50 pin, and we'll just have some hanging off the end, like we did in the first build, to be honest. And the only one thing I've got missing from here is the programming header here, because I don't actually intend to solder that on. All the capacitors, the diode and the resistor are 0805 size, incidentally. Okay, so you've seen me do these SMD builds a number of times now. Check out some of my previous videos, so I'm not going to dwell on it too long, but suffice to say that I'm going to start with the CPLD, because if that goes wrong, I can toss this board and take a spare. It's the most complicated one to do, so let's kick off with that. So pretty standard beginning. The little dot in the corner of the CPLD indicates pin 1, and the slightly longer line, well in fact it's the only longer line, in the corner on the silk screen indicates pin 1. So that's how we tell that apart, and then we just line them up by eye. Check the alignment, anchor the opposite corner, and we're now ready to drag solder the remainder of the chip. This time we go for a lot less solder on the end of our K-tip. And we look to flow along, running it a few times. When you get a blob, don't know if you can see that, but there's definitely a blob at this end. We just try and bob in out a few times, having cleaned the end of the tip off. And that normally rectifies the problem fairly swiftly. Sometimes you'll find the blob is simply too large to get rid of with this technique, and that's because in this case it was the anchoring blob. So just a tiny little bit of dab with the desolder wick. Another reflow. Problem solved. If you don't have a microscope when you're doing this work, I use a head-mounted loupe personally, then your smartphone's camera and a lot of zooming in can be a quite excellent diagnostic tool to see whether you have got any bridges there. It's a lot easier actually once you clean the flux off. Now for the LDO, the regulator, there are two footprints on here. Now that's because there's two quite common pinouts for these little 3.3 volt regulators. Now my preferred one, I don't say preferred, the one that I tend to have in stock most commonly is the LM1117. Now the key thing about that is that the center pin here, pin 2, and the tab here are the voltage out. So it takes 5 volts in, down converts it to 3.3 volts by burning off the excess power and pushing the 3.3 out of the center pins, ground being the other one. Now there's another layout where the center tab is more normally ground, and it pushes the V out, the 3.3 out from an end pin instead. So here you can see that we've got 5 in, ground, 3 out. So for, you can see here we go, that's the 3 and you can see it joins those two. So for an LM1117 style layout, then we solder in U1, and for the other layout we solder in U2. I tend to go quite bucket solder on these parts. Don't see there's any harm. The pins are huge, so I add lots and lots and lots. Make sure they really anchor onto those pads. Now the big tab at the back is used for thermal dumping as well as electrical conductivity. In fact, the electrical conductivity is not really needed. We've got one here. So let's also get a bit of flux in there and make sure that flows nicely. Now when you have a little SMD LED here, they come with an arrow printed on them. and it's very difficult to see. And basically that arrow points towards the end of the silk screen with the lines. One half of the chip has lines around it, of the package has lines around it, and one half does not. The arrow points to the lines. Oops, I've tagged a resistor pad there. I don't mind that these are a bit crooked. Gadget UK 164 will go mad. All the capacitors, as I mentioned before, the same value. And then it take a few seconds to do them all. I haven't talked you through the 0805 soldering technique I use here actually. I've done it on other videos, but I'll do it quickly now. So what I do is put a bit of flux on the pads, hold the chip and the component in an appropriate position, and tag one end. So a little bit of solder on the soldering iron. That will be floating off the board slightly. So once it's tagged, I push down on it vertically and solder in again, reflow it, and that will, you'll often hear it go click as it then sits nicely on the floor. Spin around, you can get the tip in there, a bit more solder, and holding it down again, flow the second side. And again, I'm not too concerned about the slightly higgledy-piggledy and off-axis nature of those. Others, on the other hand, maybe. Right, now the bit that I really don't like, that's all the through-hole work. So the host connector goes on this side, the side with the silk screen here. And you can see it has pin 1 at the top here. And this is just a standard 2mm pin header. We pop that in, and it takes a lot longer. I'm sorry, it does. It's not as straightforward as SMD, in my opinion. Get some flux in there. Bucket loads of solder because it's through hole, and we'll just anchor some in the middle there, I think. Seems straight enough. Okay, we can go. I'm going to be honest, that's extremely inelegant, and I really could not give two hoots. Now, as with the previous incarnation of my IDE adapter, I struggled to find a 44-pin socket. And so I've just bought 50s, and we end up with an overhang at here, which I could trim off. It doesn't worry me that much. But what I tend to do is I tend to make sure that pin 1 is flush, and so I know that the overhang here is the other end to pin 1. He's jamming quite tight because of that overhang, so I'm just going to mount both up, I think, and try and do them at the same time. You see, you have to bend. Maybe you have to bend that overhanging pin out a little bit, which actually means it's quite tightly jammed in there. So that's that does make it good for soldering. Now, the way that this master and slave arrangement works is basically only if you have two devices capable of using the chip select, the cable select master and slave arrangement. And what they'll do basically is you ground up a pin on one and you leave open a pin on the other, and that just indicates to the attached device which one it ought to be. Now, obviously, if your device has master and slave jumpers on it, then you can put them on any header you like. Doesn't make any difference. Unfortunately, my SD card adapters don't support, they're just always master, they don't support the either a jumpered selection or the cable select. So this dual drop is not really particularly useful for the use case that I have, but if you do have a real device that has either a master and slave setting or a cable select option, then you can now have, for example, a permanently attached boot device and an easily swappable SD card. I think most of the CF card adapters support master slave, but the SD card ones that I've seen don't. And there we go. What's that taken? A little over 20 minutes? Now the hard part, we've got to clean it up.
Now, would you believe it? PCBWay have just turned 9 years old. They've been sponsoring my channel for the last year, which means that they've been sponsoring me for 1/9 of their life. Quite amazing when you think about it. Now, as you'd expect from a company called PCBWay, PCBs are their stock in trade, and they really are top-notch in that regard. They've produced every one of the PCBs that I've featured on my channel in the last 12 months. But as I've been telling you over the last year, that's really not all they do anymore. They can offer you CNC machining, 3D printing, sheet metal fabrication, and injection molding, all right here from the website. If soldering's not your thing, they can even assemble your PCBs for you. Normally get a man in to do that. Do please have a look at their website. They are really a one-stop shop for all your maker needs, and I do wish them a very happy 9th birthday.
Right, so the next step is to program up this bad boy. This is the command I'm going to be using. xc3sprog -c jtag hs2 high speed 2 position 0 in the chain verbose IDE Auto-Swap JED. IDE Auto-Swap JED is available from the repository, and that's the already built firmware. Now I use one of these. This is a knockoff Xilinx programming cable. This is relatively expensive, costs about 30 quid. There is a way of doing this with a Raspberry Pi, which I will I'll link in a video too if I can find one. But this is the technique I use. Now, if you are just deploying, you know, an already tested firmware, you're not developing, i.e. you're not flashing this loads and loads of times, then there is a trick where instead of soldering on pin headers there and then having to remove them again, or having pin headers flapping around all over the place forevermore, if you take your JTAG connector here and attach it to a loose pin header like this, then you can kind of just sit it in there and apply a little bit of sideways pressure, and that's probably enough for the few seconds it takes to flash. So this is connected up to my virtual Linux box. We've got the command all teed up, but we can't just flash it like this, unfortunately. By the way, pin 1 is at this end where it says J2, and that's the red 3v3 line. That's only a detect line. It does not power the chip. You'll see this red light does not turn green when I attach this and try and program it. We need to get 5 volts into this board. The easiest way to get 5 volts into this board is to actually just put it in the Falcon. Okay, now this is one of those occasions where number of hands required is fewer than number of hands available. So this could be quite tricky. But basically what we've got here now is red on the cable is pin 1, goes to pin 1 as labelled on the host connector side. And that should provide 5 volts through to, when the Falcon is turned on, 5 volts through to the regulator, 3.3 volts through to the CPLD. This is not cleaned up very well. It needs a proper soak. Red, as I said before, is pin 1 again on the JTAG connector, so we'll slot that in there. And just bring this into shot. So what should happen is when I throw the switch on the Falcon, this should go green. I'm going to just, again, this is where the hand is required. Can we get that all into shot? Try it like this. There we go. So when the switch is thrown, we should get this light, this LED going green, and once it's gone green I'm going to press enter on my laptop down here and hopefully it will start the program. So power goes on, status light goes green, I'm pressing enter on my program and it's saying programming sector and it's counting up 30, 40, 50, sorry this is off camera but really not enough hands again, and we're up to 90, 100, 107, verifying, done, power off. Programmed. Okay, so now what can we actually do with this? Well, I have here two SD cards. This one is my normal Falcon SD card. This contains all my normal operating system items, and this is in the normal Falcon Big-Endian format. If I pop this now into my laptop, I won't read anything. This is exactly the same data stream, except it's been byte swapped on the laptop. So this is exactly the same information as this, but in the reverse order. So just to prove that we can boot up, first of all, let's pop the original card into my IDE to SD adapter, and we're just going to put this directly onto the Falcon's IDE connector. This has a pin 1 label down in this corner, so that goes onto the red side. There we go. Now, if we power up, try not to short anything. Now, if we power up, should see the screen come on. Okay, well, the screen did come up, but I ran out of storage. So here we go again. Screen has come up. There's the memory test. And there we go. My hard disk is auto booting. Some activity flashing on there. There we go. We're into our normal operating environment. So what I'm going to do now is take out my SD card adapter and now I'm going to mount it into my IDE adapter. So pin 1 down this end, going to put it in the master, doesn't really matter because it's by itself, but I'm going to put it into the master slot there, and now I'm going to put this pin 1 into the Falcon. Remembering that we still have my standard hard disk image in the adapter here. Try and balance this in such a way. Maybe if I do it, can I do it this way around so you can see the activity light? Poke under there. Is that in shot? Just about. It's very difficult to, I'm in a tiny shed, it's very difficult to frame this. Okay, so I'm going to throw the switch again this time. Now, what we should see, there's a little flash there from the activity light. What we should see is it boot up, but it shouldn't find any partitions this time. We should just fall through to the desktop. Get another flash of the activity light, nothing happened. Right, well, we're expecting that because this is the normal Atari Big-Endian image. So let's swap it over for my byte reversed copy, and we'll try that again. So a little flash of green for the activity light there. Up comes the memory check. We'll skip that. Now we go flash for flash green and we boot back into our environment. Great, but well, hold on, what's changed? That was what we just did, except now we've got all of these components in the way. Well, that's where the next bit comes in. Okay, so back we are at the laptop. Now, this was my original Falcon byte order SD card. I'm going to pop it into the reader here. Now we're on the Mac here, and you can see it just pops up with the disk attached. It's not readable by this computer. So we can open the disk utility. Yep, we see nothing. That's what normally happens with the Big-Endian image. So this is the Little-Endian image, swapped order image that we just set up. Let's try this one out. Immediately we see a whole host of drives appear. 536 megabyte drive, disk 2S1. Now they're all called no name, so this is disk 2S1, so this is drive C. We'll rename that to drive C. And now if we go to our drive C, well, there are our files. Perfect. I can test this. I'll create a text document here and type something out. We can see hello text has appeared here on our drive C, and we can eject that SD card and take it back to the Falcon. Okay, so we'll pop the SD card into the IDE adapter and we'll power on. Boots up as we've already seen. And we should have new file, hello.txt. Perfect. So how is this magic possible? Well, there is a trick and there is a limitation. So the important thing is that when this SD card was partitioned by HD driver, which is my driver of choice, it was set up with a special dual compatibility option, TOS and Windows, and that can be configured in here under compatibility. So it's compatible with TOS 1.06 and it's compatible with Windows, but there is no byte swapping enabled. If you enable the byte swapping, it can't auto boot, and that's always the problem with software-based byte swapping with HD driver. EmuTOS can do it, but then it's slow. Here there's no byte swapping because it's all done in hardware, but the compatibility layer is there. Now there is a limitation. I didn't show you it in Linux, I showed you it in MacOS, and that's because Linux actually doesn't like this compatibility mode. It plays a little fast and loose with the settings, and that's with the configuration options in the partition table, and Linux balks at that. MacOS doesn't, Windows doesn't. That's the reason why it's there. So it depends really on your use case, but for me, copying large files from MacOS onto the Falcon's hard disk, which I can then pop in and boot, is ideal. Hello, it's David from the future here. I realised while I was putting this together that I only showed you this working under macOS. That's because I didn't have a Windows machine available, but I thought I ought to show you that because that is most people's use case. So I fired up a very slow virtual Windows machine here, and I'm just going to connect up that SD card that you saw me using. There it goes. You heard Windows recognize new hardware edition. So if we sit, here we go, and wait for this to work out what it's doing. There we go. We've got one of my Falcon drives up there. They have, oh gosh, there's a lot of drives that are mounted. There we go. That's the C drive. There's the auto folder. It works beautifully, and that's E F G H I J K L. Yeah, that sounds about right. So that basically behaves exactly as I showed you under the Mac, but under Windows. Now we've seen in the past that EmuTOS can handle not only byte-swapped partitions, but also PC formatted partitions and Linux formatted partitions with aplomb. You don't need to worry about any of this stuff. So why are we not just using Emitos? Well, there's a couple of reasons for that. One, unfortunately, Emitos doesn't currently yet support the true color modes on the Falcon. That's a big sticking point. Otherwise, it's completely usable in most regards. And the other one is that when the software does the byte switching, there is an overhead. And I've run some statistics in my previous video showing the speed difference, and it's quite noticeable. I'll put a little compilation here up at the end.
So what benefit does using the twisted cable actually offer? Well, the simple answer is speed. Now, what I've done is actually run some comparisons, and I'm going to put them on the screen just after this. But you can expect to see, depending on the speed of your processor, because the faster your processor, the quicker you can swap those bytes, you can expect to see between, say, 30 and 500% increase in disk access speed by using the hardware swap.
But this technique, with HD driver, with the automatic byte swap, you can just rip the card out, pop it into your Windows or MacOS machine, copy the files across, and put it back. So there we go. That was a really quick build, a nice, neat little project, and one that I hope is going to be useful to people. There'll be a link in the description down below to my PCBWay community page, which has all the details necessary to build one of these. And the entire thing is open source, as most of my projects are. And you can find full details, including the schematics and the Verilog, on my GitHub page. I should say that whilst I did have this idea when developing the old byte swapping board, Christian Zietz actually developed a very similar product to this in the past, but for larger 3.5-inch IDE connections. Now, my project is not based on any of his work, but the fact that he could do it and he had implemented it did spur me on to set about building this up. I was confident I could make it work. So whilst my work is not based on his, I suppose you could say it was inspired by his. So I do feel it only fair to mention him. So thank you very much, Christian. But this is all my work. It's all on GitHub. It's all available open source, and it's available to order on PCBWay. Thank you very much for watching. I hope you found it interesting. I hope you found it useful. Give me a big old thumbs up, and I'll see you next time.